Hey everybody, it's Obi-Wan Pez for N Simplex Pachinko, and we're going to do some math tonight. We're looking at continuing our pre-calculus curricular stuff. Probably finish some be working on, what are we doing? Right. Finishing up rational functions. And Alright, got our pre-calc book that we're looking in. That is OpenStax Precalculus 2E. It's been the one that I've been teaching out of for the last probably 5 years or so. Maybe 10. Time is all wonky and stuff. And generally speaking, OpenStax has been doing good work over the past, well, since its inception, but I've only been paying attention for the last about 10 or 15 years. Somewhere in there, not exactly the whole time. For quite a while, we were working on off of Pearson books, and I think when our developmental program moved from Pearson to Newton, was roughly the same time as when our pre-calculus courses ditched Pearson and just went to OpenStax, because it's free and we don't have to keep getting yanked around by a publishing company. So not that there's anything inherently wrong with the publishing companies. They have to make money on what they have, otherwise they can't stay open. They can't have staff and whatnot. But promising us subscriptions to their services at a certain price and then raising them in subsequent semesters, and saying that they're not going to do that and then doing it anyway, we just decided we were done. So we went with Newton for the LMS, the Learning Management System, and kitted it to fit with our Canvas courses, and everything went smoothly enough. Nothing was 100% perfect, but it never will be. As evidenced by our differential equations class, which our coordinator for differential equations spent probably an entire year kitting the MAA system, WebWork, coding WebWork to house, all of the differential equations homework, which was a nightmare at the time, but it worked really well, and it's a real testament to this particular person that he was dedicating himself to be able to do that for, like I said, a full year or something like that. Yeah, I was really happy with the work that he had done with that. The students constantly complain about web work. Most of the teachers also complain about web work when they don't, that they have to like go in and correct it because it's wrong often. But the problem is, most of the time, that the students did not know how to code stuff in web work. And it was like, I missed a parenthesis or, put a space in the wrong place or something like that. And it just marked them wrong. And it's like, no, you're not wrong. It's just, you need to be a little more diligent about how you make all this stuff work. Okay. So we have irrational functions. That's going to be exponential to logs. So here we want polynomials, rational functions, equations and inequalities, right? In addition to rational functions, we want root. Meow weather. Yes, if you're at all interested. Right now I'm doing some curriculum development, but I will always take some extra time for anybody who wants to learn a concept. So let me know what you would like to see, and see what we can do. Generally speaking, I teach up through, give or take, differential equations, which is generally middle of college for somebody who's going to major in a STEM field. Anything under that I have taught over the last 15-ish years. So let me know if you're interested. And
We don't have enough staff to clean a whole office block, I'm afraid.
Meg's new cleaning firm has been turning down some big jobs. To ensure it doesn't happen again, she needs to get her hiring done and dusted.
But I'm hoping we can be of service very soon.
Indeed can help her find great people fast. Indeed you do.
okay, definition of root functions.
More tools that save time to help you hire quality people. Inquiring, visit indeed.com/try today.
No internet? No worries. With Spotify Premium, you can download the songs that move you and take them offline, wherever. Get 3 free months before it ends. Cancel anytime. Tap the banner to learn more.
Okay, we're going to do definition of root functions as rational exponents. We'll look back at... actually... Look back at the square and cube root functions that we already talked about in terms of function analysis. And then we move up to looking at those root functions in terms of being rational exponents. So this is like x to the 1/2, x to the 1/3, being for square and cube root functions. And then we can start talking about all of the different values that we can make that have. So we can start talking about parity of rational values, or parity of the numerators and denominators, and figure all that stuff out. Okay, so yeah, can work with that. Let's see, so if we go in Kill the canvas. Alright, so going back to, like, Aristotle, like, way back in the Greek days, oftentimes what would happen is that you'd be able to look at just literally a shape, right? And you look at this as, okay, well, we have a triangle. So we're going to do a super simple example. Aristotle was like, okay, for stuff like this, we could figure out how to find the area of this particular triangle because we already know what the base and the height are, and then we know that it's going to be 1/2 the base times the height to get the area. Super easy. Right, now, granted, at the time they didn't have algebraic formulas, but nonetheless they knew to take the numbers, take their products, and then have them, and that gets you an area of a triangle. So then the idea comes that at some point they're going to want to figure out, and also these are Cartesian coordinates. Made popular by René Descartes in around the, what, 1500s? So, like, this is way after Aristotle. Right? Right. Algebraic manipulation, aka algebra, is from the 11th century. So again, this is way after Aristotle. But the idea, nonetheless, was if we had a, like, Greek perspective on this, how do we figure out what the area of a circle is going to be? In this case, a quarter. How could we come up with the area of a quarter circle? Yeah, we know that it's going to be 1/4 pi r squared, but, like, can we do better? Can we find a, you know, formula for it coming from something? Right, so the idea that Aristotle and many of the other mathematicians, not Socrates, Archimedes had was, if we go back to our previous example, we could take our triangle and we say, like, okay, if we were to take a giant freaking box that goes around this thing, right? Make it a rectangle. This is a terrible approximation for that shape. Right? Fair enough. That's a terrible approximation for that shape. But what could we do to make it better? Well, we could instead cut it in half and take an approximation of two separate rectangles. Right? So, again, still a bad approximation, but it is a less bad approximation than it was. So, let's keep moving with this. Let's not just do those, let's split those in half as well. And then here, this is going to be there. This is going to be here. This is still going to be here. And this is going to be here. Again, still not a great approximation, but now we've eliminated this rectangle here and this rectangle here. So we've eliminated these two chunks and we've cut down this box here. Right, so now we've got like this stair step that's getting a better and better and closer approximation to what we had before. So somebody was like, okay, look, we can't just like we can't just keep doing this forever, but like in theory, what if we could? So it wasn't until the 1300s that the ideas really started getting laid, and then in the 1600s when Isaac Newton and Gottfried Leibniz came around, that they had the actual framework and mathematical notation to support the idea. So the idea, again, going back to Aristotle, Archimedes, and whatnot, is let's take even smaller and smaller and smaller rectangles and more of them. So we're going to eventually get something that is like these tiny, tiny rectangles like this, and then literally make them as small as we possibly can. Until we eventually get something that is infinitesimally larger than the area that we actually want to get. So in here, we're saying, okay, we're going to take the area of each individual rectangle is going to be the base times the height of each of those rectangles. Now, what on earth are the bases and heights of each of those rectangles? Well, the bases are infinitesimally small, right? They're as small as we want to make them. We can call that delta x, for example. Right? Make those bases individually some sort of horizontal distance that is the change between the previous one and the next one. It doesn't even have to be uniform. We can call it delta x sub I, and they could all be different from each other. The bases are basically 0. Yes, not literally 0, because then it would just be 0. But we say, like, they're as small as we want to make them. As tiny as you want to make them. Still technically finite at the moment. Right? And then the heights of all of these are going to be based on the function that we have. So if we go with this and say that this line here is going to be f of x. Now, it's a line, so it's super easy, but what if we let f of x be a curve? Right? Now we can make this as complicated as we want. It no longer has to be just linear functions, just nice shapes. We can make these shapes as convoluted and crazy and like wobbly as we want. All we have to do is make sufficiently small rectangles, and we can find the area that we get from those rectangles. So our height is always going to be, in this case, the f of each of those x sub i's. Right, so going across, we just get like x1, x2, x3, x4, x5, x6, all the way out as far as we want to go. So the area of each rectangle is now a sub whatever. So we call it a sub I to generalize. And then we say it's equal to our f of x sub I, which is how tall this thing is, times delta x sub I, which is how wide this thing is. And then what we need to do is just sum them all up. Take our I, we go from 1 to n, however many we're making. Now the question, I guess, at this point is, where are you in your understanding of sums, sequences, and series, and limits? Mm-hmm. So, series and sequences, generally speaking, are pre-calculus level. If you haven't seen them before, that's fine, you know. But the idea is just to say, we're going to sum up all of these things. Basic algebra, okay. That's all right. So I'll give you the brief thing. We don't need to worry about it technically, right? We don't need to get all of the technical details in. Yeah. Just to let you know, right? We have a bunch of math people in our community, affectionately known as the Math Chads. All of these people will stream some sort of mathematical topic. Some of it may be programming or applied math, etc. But literally every single one of these people here will stream math and probably give math help if at any point you do want some. There are more people than this. We also have a central Discord server, which is here if you're interested. If not, don't worry about it. No worries. But we also have links in there to the mathematics Discord and math help Discord and things like that. But okay, so the idea here, thank you very much. So the idea here is that we're going to take all of these rectangles, no matter how big they are, and we're just going to add them all up. And again, as long as our rectangles are sufficiently small, then we will get a better and better approximation of the total area. It won't be 100% accurate because these are still rectangles on a curve. Or at least they won't likely be 100% accurate because they're rectangles on a curve. Or rectangles on a straight line that is not horizontal, right? It's going to go like this. It's still going to have like this overhang. Okay, so what we do next is we take something that's called the limit. And what this does is it says we're going to let the number of rectangles go off to infinity. There are going to be an infinite number of rectangles, which means that each of those individual rectangles is going to be infinitesimally small. So now it's basically going to look like a computer picture, where we just have a single file line of pixels going from the top of the curve to the bottom of the curve, or to the x-axis, right? From the top of the curve to the x-axis, one single line of pixels. And we move over, and one single line of pixels. Move over, one single line of pixels. No matter how much you zoom in, you always end up with just one single line of pixels that counts up all of that area. It might be a little weird. It's fine. So we go from 1 to n, where n is going off to infinity of this f of x of I times delta x sub I. As long as, again, our n is going to infinity, we've got an infinite number of these rectangles, and they are each infinitesimally small, then we can get an actual value for what is under these curves. Not just an approximation anymore, an actual value. So, what we can do is we can take what's called here, or this is what is defined as an integral from the starting location A to the ending location B, wherever those are. Now in this picture here, it would normally be just A to B, beginning to end, but we can put those anywhere we want on this curve. As long as it's within the domain of the curve, as long as we're not going somewhere undefined or not allowed. So if we let B go any further than that on the circle, then the circle doesn't exist over here anymore. So we can't do that. But as long as it's within the circle, right, we could have A and B be at those two locations. Then we only want the area between here and there, which also presents an interesting possibility, we no longer need these special formulas in order to calculate stuff. We could get the area from here to here along this curve. Right? Let's calculate that instead of having to rely on just a quarter or just a half of a circle. Now we can get some weird amount like that. This is the power of calculus over the continuous mathematics that we see. Wow, awesome. I didn't think I was going to be able to pull that off. All right, anyway. So here we take the what's known as, again, integral of f of x, and then when we shrink delta x into an infinitesimally small interval, we call it a differential. So that becomes dx. When we do this, now we get the exact area that is on that curve, or under that curve. So if we wanted to do it for this triangle here, right? Let's assume for the moment that we have a function f1 of x is equal to, this is going to be 6 minus 2x. Right, so this is going to start at 0, 6 and then go down with a slope of -2, -2 over 1. That's going to end at, it's going to hit the x-axis at a value of 3, 0 location. 3, 0. Alright, so let this be 0, 6. Let this be 3, 0. That means that what we want, in order to find the exact area under that curve, is we want to take the integral of 6 minus 2x dx from an x value, x equals 0 to 3. Don't worry too much about the details again, right? You need usually like... Yeah, definitely. And this is another thing is once people take like Calc 2, they start learning how to find the centers of mass of objects and irregularly shaped objects. So, you know, a quick and dirty way to do that is just to take like a spike, or whatever they call those metal spikes, and just like put it under the object and move it around until you feel the balance work, right? That's the quick and dirty way to do it. If you wanted to do it for real, in terms of like mathematically, where do I do this? You take the area of the whole shape. Yeah, a little bit, but you'd be like... Here's a good example. Right, this is scrap left over from my kid's Pinewood Derby car, but I could stick this on the bottom here and try to figure out where it is that this thing balances. Now, this is incredibly awkward. I also don't want to drop that on my tablet. We can move it around until it actually balances properly. I just messed that up because that's on the other side. Of course, I got to go back and forth properly, but yeah, until it balances, and then you found the center of mass of that object if you can balance it, like on a point. This is an awkward point just because it's half worn down because I've been writing with it for 6 months, a year, something like that. But like I said, you know, irregularly shaped objects. You could grab some irregularly shaped object and try to find, or irregularly dense object, and try to find its center of mass by doing the exact same thing. Again, it's awkward when you try to do it that way, and then when you do it mathematically, you could say, I know exactly where it is, it's, you know, this distance from this side and this distance from that side, right there. And draw in the point, do a snap line or something like that. And then put a punch like right in the middle, or, you know, where the center of mass actually is. My dad used to do all sorts of stuff in order to find centers of mass. I think actually he would hang it like a pendulum. He would hang it from single points and then do a snap line, and wherever the snap lines would line up is going to be the center of mass. So that's like another cool way to do it. He learned the cool way. I learned the completely dorky way, which works 100% of the time, but like it only works with ideal solids. Alright, so let's say this is going to be 6x minus x squared. Evaluated from 0 to 3. This is going to get us 6 times 3 is 18, minus 3 squared is going to be 9. So this is going to be 18 minus 9 is 9. Right. So then what we do is we can look at this and say, okay, for this super easy example, right, the height is going to be 6 because here we have 0, 6. And the width is going to be 3 because that's 0 to 3. So 6 by 3 is 18, and then we have it, and it's 9. Again, super easy example because it's just a linear function. I already know how to do integrals, and then we just plug in the values and you get what you need. So 9 square units for this particular thing, you know. 9 square inches. But then we come over here to the circle, and it ends up being a bit harder, to be fair. So circle has an equation that is going to be y equals the square root of r squared minus x squared. And we end up having to use some fancy trig stuff to make this work properly. But it's not terribly difficult, it's just more involved. And again, you end up with a function which is going to get us this particular area here. And it works out so nicely. Oh, yeah, if you go back into VODs for, I think, last week, my dad set me a problem. I found out what it was for. So they have these wire baskets, which are just, you know, standard circle, and then the middle has a little hangy thing that they grab it from. So just a standard, you know, 2-inch ring. And if essentially, like, the original purpose, I think, was condiments. So you just put your, you know, ketchup, mustard, whatever in the basket and then pick it up like that, and you could carry it around to whatever table. So what they did was they co-opted this. This is a brewery, and they co-opted it and put like little catchers going around the sides to make sure that their sampler glasses, little 4-ounce ones, don't start skidding around all over the place. So they put their little samplers in like a nice little holder that then you can pick that up and the glasses stay in, what did I just do? That. Stay in this arrangement. So generally speaking, there's one here, and one at the bottom. Right? So 1, 2, 3. So he was trying to tell me about this without, like, telling me what it was for some reason. And he's like, okay, so he's a woodworker. What I want is to be able to have, you know, these 3 circles, which are this big, be at the corners of an equilateral triangle. Then I want to draw, like, equilateral triangles off of that one equilateral triangle, and then put circles at like the corners of each of those. So essentially it looks like this. And so I drew this out using some of my, like, I've got precision tools that I just keep in my desk drawer here in case we need them. You know, compass and straight edge. Every mathematician almost certainly has some. So I drew that out for him and sent it over, and he was like, oh yeah, that right there. And so like I made 3 different sets of curves. One was like, okay, so if we draw those triangles out like that, then the first one was if we take the, what is that? Okay, so we go from here at the center, drawn out to the other triangle, and then just use that as an arc. So we sweep across, it hits both of the corners of this triangle. And we basically cause the wood that he's making to go from the glass and then swoop down into the middle and then come back up. Reason being, and again, he didn't tell me, reason being, what he wanted to do was set another one in here, like in this spot. So I would have made it actually significantly deeper. I ended up sending him prototypes which involved a catenary. So that's as if you were to hang a piece of string by 2 points, and whatever that dip is, that's called a catenary. And we use it with hyperbolic cosine functions. And he was like, yeah, that's kind of nice, but not really my thing. And I was like, okay, well, we can do this like from the outer triangle to the tangent of the circle. We could do this, it's really shallow. And he's like, no. And then we were like, okay, so go from here to the midpoint of those 2 things. So we like have half the distance between them and then make an arc there. And then he was like, that's alright, but you know, this one's better. And then I sent him another prototype, which was just a parabola that went between the 2. Like, mathematically, I figured out how to make that dip so that it was tangent to both circles and dipped in. And finally, he was like, that right there, because it gives him enough room to put that other glass in the middle. So finally, I went up to see them this last weekend, and they took me to the brew pub, and they were like, this right here, this is what I wanted you to see. And so I saw the original, and then he was talking about his design. So the purpose is this place is called the Czar, C-Z-A-R, and it was some joke that like the owner was called the Czar by a bunch of other people because he would always like wear some stupid hat and like be in charge of stuff. So when he opened his own brew pub, he was like, we'll just call it the Czar. And it's just like this weird inside joke. So what they did was they have a sampler rack, the 3 going around, and they call it a crown. You can go and bring that around to the tables. I'll just order a crown for, I don't know, $10 or something like that. Nah, it can't be right. Whatever it is. I'll order a crown for $6. And then he was like, we've got the Kentucky Derby season coming up soon. And he goes, all right, look. When somebody comes in and wants like all of your beers just to try all of them, they're going to have to order like 5 separate crowns, and that's just a huge amount of space, which we did, by the way. Me and my brother and my parents split a rather ridiculous amount of It'll probably work. So it's this, right? It's just a kind of ridiculous amount of beer. It's like 15 samplers, which are only, what, 4 ounces each or something like that. So, 60 ounces, but there were 4 of us. So we managed to split this amongst us. And so he was like, okay, so what we want is if we get 3 crowns, we call it the Triple Crown. I was like, all right. So you get 3 on the bottom row, 3 on the middle row, which are offset from those, and then 3 which are offset from those again, so directly over the original 3. And then on the top, they put a, like, instead of just being a ring, like a metal ring that you stick your fingers through, you put a large crown that's made out of metal and, like, attached really well, so you can slip it in between your fingers and then lift it like that. So it ends up being, I don't have a good example of that, but yeah, it ends up, you slide your hand in like that and then pick it up this way. And he was like, yeah, it's great because you can, purchase 9 of their 15 beers all at once, and they'll give you, a slight discount on it or whatever because you're buying a lot. But it's such a pain in the ass to have to pour out 9 samplers. Like I said, we had 16 of them, or all... That's divisible by 3, so that wouldn't be... It was 16. We have 1 extra. It was such a pain in the ass to have all 16 samplers poured out. He was just... The guy behind the bar was like, you're lucky it's slow. We're also lucky that we like you and you've done work for us. Because he's also... so my dad did... he helped them open their second location. And he had, like, the template of what the bar rail should look like. So it's this... it's got 3 stripes of a lighter, like beechwood or something like that, and then 2 stripes of a really bright cherry. So it's like, I don't even know. Like, I don't think I can replicate this, but it's slightly darker than, like, fire engine red. But not to, like, burgundy or something. And so it's 3 stripes of light beechwood with 2 stripes of the burgundy in between them, and it's 40 feet long and then it does an L shape back into another 10 feet back, and I'm like, oh my god. It was very impressive to see it. Or at least, I didn't even see their second location. I saw the original in my hometown, and then this is in New Hampshire. And just like imagining, how big is this thing? And he kind of like showed me how large it was in relation to the place. I'm just like, that's insane. So yeah, the power of calculus here really is in using irregular shapes and doing things that, again, don't allow you to just use a formula. Because again, just using a formula, very cool, very easy, but doesn't always work, unfortunately. me think real quick. Because, like, there's an easy way to do this, too. I'm just thinking. If we were to do just radius is equal to 4, right? We could do this as a polar from 0 to pi over 2. We're just evaluating 4. And instead of using vertical rectangular slices, one of the things that we can do is make sector slices. So this is going to take this so close. I'm alright. Nope. Close enough. This is going to take this and do a slice going this way using our angle, which can be delta theta with our r's here. So again, the equation that we're using is just r equals 4 is going to be a radius for circle. And then we're going from an angle. This here is theta equals 0. And this here is theta equals pi over 2. If you do like pre-calc stuff, figuring out angles is a little bit different. So instead of doing degrees, we usually use radians, which is what this is. So we go from a like how many radii are we wrapping around the outside of the circle. So here is approximately 1 radian. So if we literally take the radius of the circle and then wrap it around the outside of the circle, that's how far we get, give or take. And then when we get up to the top here, this is actually pi over 2 radians, which is 1.57 some other stuff. So then when we do this, this gets us a 4 theta. Just going to go from 0 to pi over 2. Unless I screwed it up somehow. I don't know. I'm probably fine. Right, pi over 2 times 4 is going to be 2 pi. And if we look at area equals 1/4 pi r is 4 squared. Ah, crap. Well, that's not good. Right, that's going to be 16 times 1/4 times pi, so that should be 4 pi. Alright, so I'm off by a factor of 2, or I needed to square something. It's not just the number 4, right? Because we were taking the thing where, hang on, polar. Polar integration. Okay. That's annoying, but yes. So it turns out it's 1/2 times the radius function squared. There's a whole bunch of reasons why this happens, and we're not going to go into it because that's a Calc 2 thing, and it's way far down the line there. This is going to be a 1/2 times 4 squared is 16, which is 8 times theta, which we can make it 8 pi over 2, which is 4 pi. Okay. Right. So I just forgot there are reasons, hand wave. If anyone's interested, we got right, definition of how to do integrals of polar functions, including the entire argument, starting from, we're going to find the area of this sector, and then sum up all the areas of all of the sectors. So, I mean, there is an infinite amount I guess there's a finite amount of human discovery, but there is a potentially infinite amount of, like, stuff out there to still poke around with. I'm still struggling with a lot of concepts that are, just out of my reach. So I earned a Master of Science in Applied Math in 2010. So it's been 15 years, and I'm still plunking away at trying to figure out some extra stuff that maybe I don't need, but you know what? It just seems like it's fun. I was also gifted a number of, I say a number, I was gifted 10 boxes of books that came from an old calculus professor's stash. Yes, these are just 3 of the books, but there were, like I said, 10 boxes of books like this. And I mean, when I say boxes, most of them were your standard, like, office paper. So, what? 16 inches by 12 inches by 16 inches, give or take. The same sort of stuff you see. Same stuff you see dejected office workers leaving their offices with their potted plant and everything, in television and movies. But also, there were multiple which were the size of... I've got a piano bench sitting next to me. This is probably about 30 inches by 16. Like, that big. By that big. By that big. At least double the size of the other boxes, maybe triple. And, like, I was just like, you said a few boxes, and he was like, like, what the fuck, dude? So I took them, and, like, I just went on to Abe Books. I was like, how much are these actually worth? Because I don't want to just throw something away that's maybe priceless. And I felt like if there's something that's over $100, like, I should let him know. Because I don't want to just be like, I've got a ton of money now. So I found one book, which I can't remember exactly what it was anymore. I could probably look it up in my texts or emails or something, but it was worth, according to Abe Books, it was worth $750. And I was like, I do not want to handle this. Like, I'm not carrying gloves. Like, I should wear gloves while I'm handling this. And I was like, you should have this. And he was like, yeah, I think, like, you know, I'm perfectly happy for you to sell it. And I was like, no. No. That is too much, and maybe you should have it. And he was like, that seems pretty cool. And he's also an engineer. So, like, just having it in his office is kind of like a badge of honor. So he was like, I'm probably just going to put it on display. I'm like, that's fine by me. Your dad's books, right? It's but I was going through, you know, probably nearly 200 books. Like this one is vector and tensor analysis. I have it marked as it was going for $60, and there were just, like I said, there were so many of these, but at the same time there were a bunch that were like, 35 cents. So I was like, okay, I don't feel bad about chucking that in the charity bin. Ads are about to start, so if anybody is hanging around, I'll be back in 3, and we'll do some probably Eskrima again as a warm-up, or getting into the next section. So see you in 3 minutes. Thank you so much for coming.
Ripping harder, more less. Never stop, no rest. Till the stress is breath in my chest. Till it's diamonds wrapping my neck. Progress to a god from a god. Mass hopeless, more tests. More blessed. Dug deep down, trying to find my best. Find a beast, had to kill a conquest. I'm next. I'm too on till I'm too off. Come down, make new thoughts. Like jumping off of that rooftop. Hold my camera when I do not to make moves based on my mood drops. Like who's lost? Like who's lost? It's yours. Steadily killing me, running my brain full of shame. I don't wanna lose it. Full of stage, trying to run my pain. See sun coming out of that rain. My team, really my team. I'ma never slow down. I'ma never behave. Stuck inside this prison, inside this cave. It's taking over.
All right. For anybody who hasn't been around before, welcome. So my name is Obi-Wan Pez. This is N Simple Pachinko. We do math content every Mondays and Wednesdays. You know, schedules pending and all that. And we do gamey type stuff on Fridays. I'm going to be taking a break next week because my family's moving. My family is taking a vacation to Scotland, so we're going to have just some vacation relaxing time. Unlike this last weekend where I was just away with family stuff going on. So we're going to be doing just relaxing and hanging out at we're going to go to Inverness and Loch Ness, and then we're going to come to Edinburgh and spend the rest of the week there just kind of relaxing. So we're doing kind of like a 3-day, 4-day thing at pretty much everywhere that we go. It's kind of amusing. This is a martial art known as Eskrima, which is a Filipino machete martial art. Also has uses with Chinese broadsword. And our instructor also is a borderline master of Tai Chi, so he's also been teaching me Tai Chi on the side. It's been going really well, just all of it. He's got a really good knowledge base, really good attitude about everything, and we mesh really well. You know, I've also been taking Tang Soo Karate for roughly about 17 years prior to moving to the UK, at which point I realized that, you know, I wasn't going to be getting much done in Tang Soo Do. Looked around, found a couple of martial arts places. Nobody called me back, so I found this guy, emailed him, and he basically sent me a message back, you know, the next day. I was like, yeah, sure, come on, stop on by. And I've been going to see him ever since. So it's been close to a year since I started learning Eskrima. The martial art side of things, again, it is an armed combat martial art. Typically, it starts with a single machete, and this is actually known as a kali or arnis stick, which helps do Eskrima. So Eskrima itself, Filipino origins, comes from... My kid did not clean up the paintbrushes. Cool. Didn't even notice this earlier. Should've. Oh my god. Dude. So typically you start with a single arnis stick, and we start in a ready position, which is more or less square, maybe a little bit forward. The hand can either fold onto the bicep on the other side or stick more in front of the sternum. The idea here is that you're going to block anything that comes in toward your sternum, because that was also a thing that happened back in the day when this was first getting started. Typically they were fighting people who were armed with small stiletto knives and could maneuver very easily and quickly, and love to stab people in the heart underneath the sternum. So the original makers of Eskrima wanted to protect themselves, so they have a block here just to make sure. Oh, I should probably make that bigger, because you probably can't even see me. There we go. I can also see myself much better. So typically we're standing here at kind of a ready stance, and then the strike out is going to involve typically holding the weapon so that it's pointing almost directly at the person. So if you notice here, this is pointing almost directly at the camera, which really hides which direction it's coming from or going to. So then we can make multiple different kinds of cuts. Most of the time it is going to be straight out, and you're aiming basically for the other person's face and then back. The other arm is also used for counterbalance, which also helps the muscles in your back and your chest not like overextend too far. There's also multiple cuts that you could potentially make. So like there's a 45-degree angle upward cut from underneath. And there's also a 45-degree angle down cut from over. But most of the time it's just going to be a simple strike out like that. Then from here, there's also a number of other things that you could do naturally. So we've done some where they've been straight strike out, followed by a tuck to an outside position over here. And again, you're going to do the same thing. Then from here, typically this is also going to be a strike out like this, where you slap the forearm, which also causes this to extend just a little bit further. So causes like a whip action on the hit. And then from here, this also allows us to return to ready position. From here, what we're doing is we're coming out like this, but then at the slap here, we redirect the baton or machete or whatever you've got, so that it comes back over the top this way. And then you're back in a ready position. Let's see. Oftentimes we'll do like a count up, which goes through all of like the different forms that we do. So 1 is a simple strike, and then we do a strike out, like a just kind of, it's not a wild strike, but you hard come across, go into an open position, and then from here we do a single this way, followed by a return to the other side. Now we're in a closed position again. Number 2 is a double strike, and then move to open position and a double strike, move to closed position. Number 3 is strike followed by an overhead and a single strike, and again move to open, we do a single strike, do a single strike, and then I don't think we move to this directly, but it might just be that. And across again to a closed position. And then we do number 4, which I'm having trouble remembering that one. I think that was we come out, tuck into an open, and then a single. A single with a return, and a single. And then we come across, we're open again, a single. It's a single that moves to a close. Single. Single move to open. Then a single again. Come across, back to close. Number 5 is a little weird. This one's a single, followed by something that goes over the top again. Single. Maybe. That's it. It's a single that then goes over the top, return back to a single, come back to an open, This is a single that then goes over the top to a, again, head bash, essentially. Back to a single, and back to close. And then I forget what 6 is, honestly. We do practically new stuff every week, so I think the next time that we meet, we're actually going over like everything that we know, which is going to be extremely helpful. Right, and then from here we've got a 2-stick method, which I was working on a little bit before ads came back. This is called Sticks to Heaven. So we do a 45-degree down angle strike and then return, a 45-degree angle up strike, and then we twist, swap with a 45-degree down angle strike, and then this returns to ready position. But now I'm on the other side. So naturally, 45-degree angle return, 45-degree angle twist, swap, and then return. So there practically is no footwork, which kind of bothers me. But there is some hip work, which is adding to the momentum and the power and things like that. And my instructor's been saying, like, you know, because of your karate background, that's been really helping. I only have a 1st-degree brown belt in Tang Soo Do Karate, but nonetheless, I have taken it probably less seriously than I could have, than many of my other colleagues. And honestly, I probably have a black belt-ish asterisk. You know, 1st degree, very small. But I need to prove myself. I need to actually do it when we go back. So, there's other stuff that we do. So we've been doing like double strikes, go forward and then reverse. There have been, let's see, one of the other strikes that we do is a fan block. So this comes from here and we go forearm and then back. Nope, that's wrong. That was what I needed to do first. We do a backhand block followed by a forehand block, and then this ends up coming around and striking through. So it's like a comma, makes a comma in the air. And that's the other thing about these. So I have 3 different sets of sticks, much to my wife's chagrin, I'm sure. So we have the 125-gram trainers, which are about the same size as the black ones I've been using. We have 250-gram polycarbonate, which are beautiful and practically indestructible. I have actually broken multiple people's rattan ones with this, just like over time. The constant hitting of plastic on wood is causing the wood to just shred. These are, perhaps slightly unfortunately, 2 inches longer, which also means that the tips end up going a lot faster. And then we have the 500-gram like performance ones. These are made out of ironwood, and so it's like super strong. If you smack these on stuff, it's very powerful. So we've been playing around with the Eskrima again, like I said, for about a year. It's been going pretty well, all things considered. We've got a group of like 3 other students who are also I think, black belts in whatever other martial art they came in from. And so it's been really interesting and helpful to like learn all of the different things. Math teacher by day, vigilante by night. Yeah, don't you know it? So the carrying of club weapons is very much illegal everywhere. I am staying in the UK for the next 2 years, and I really don't want to get like thrown into jail or kicked out. I think my spouse would be very disappointed. As would my children, I suppose. Alright. Tonight we are hashtag not sponsored. By... Who is this? Thornbridge Cocoa Wonderland Chocolate Porter. I do like the can art. It's very mathematical. I can actually see through it a little bit from my side. Oh, yeah, you get a little bit down there. So, it's a nice dark sort of ruby color. Smells very much like chocolate. And I got something in my eye. Ouch. Unrelated. Alright. If anybody does want to have any explanations of anything, please let me know. Meowther, if you have any other curiosities that you'd like to talk about, let me know. Solve area of a shape with a curve in it. So, oh, okay. So composite. Yeah. Like he said. So yeah, if you were to make some sort of shape like this, terrible. Oh my god. Something like that. I think that's all the information we need. So I'm going to go with, we want find the area and the perimeter. So this is a little bit different than, you know, people might be used to, but it probably isn't even something your teacher would necessarily assign. It depends on what you've studied. So if you're talking about composite shapes, right, this is a thing that is made up of many different parts. And all we really have to do is break it up and say, like, what things do we have in here? Sorry. Jeez. What things do we have in here that are going to allow us to, like, build a larger shape out of many different small shapes? So you could be thinking about this as, like, blocks, right? Like, my kids have a ton of blocks. If you stick the blocks together in just such a way, you can create something that looks like this. So first question I would generally ask students is, what could you make into this thing? Like, what pieces do you see in here? Now I'm wondering if they're accessible. There we go. Yeah. That's good. Yeah. Yeah, so generally speaking, that's where I'm gonna go. If we want to, like, right triangle. That doesn't quite work, but you know what? This will work. We could pretend. Ugh. Almost. Yeah, there we go. Right, reverse of that, but still. We got some blocks that we can fit together that make it look very approximately like that shape. That's slightly better-ish. Anyway, yes. I'd want to split this. So I will say I intentionally made it not a square, but yes. If we break it here, right, just at the top of this, this is going to be a 13 by 12 meter shape, rectangle. So it's really close, but it's not quite a square. Okay, so if we want the area first, let's say, how do we calculate the areas of each of those things? Right, so we can go with area of half circle, not D. Close. Area of rectangle, area of triangle. Something like that. So as long as you know what shapes you're working with, and in fact, it doesn't even matter how you break this up. So if you wanted to, you could have said, okay, this can be, you know, 2 separate triangles here or something like that. You could do that. But naturally, rectangles are easier. Right, so you want the formulas for each of them. Half circle, we already did a quarter circle up there, so right, 1/2 pi r squared. We already talked about rectangles, that's just base times height. And we talked about triangles, maybe, which is just half base times height. Yeah, we did. Right, it was the thing we did over it that way. Right, so we have all these things, keeping in mind that this is like base 1, height 1, base 2, height 2. We don't know what they are 100%, so don't always just assume that they're going to be the same numbers or same values. Show that they can be different. Or like label them on your diagram or something like that. Not super important, but... Right. So... 1/2 pi times. What is the circle's radius? What is the rectangle's base times height, or base and height? And then what is the triangle's base and height? Fizzbuzz! Good evening and welcome back in. Good to see you again. How you been? Yeah, I'd say we got some good ones musically tonight. Haven't been terribly boring, so that's good. Okay, go there. I can't take credit. This is the, what is it? Copyright-free music playlist. Currently on Spotify. Although, it's the same thing on YouTube, it's just different ad set. Area of the circle, 39.26 meters squared. Okay. I'll take your word for it. Lol. No, of course not. So, right, the important thing to do here is we're saying, yeah, this is going to be 10 meters is our diameter. 5 meters squared is going to be the radius squared. So that's going to be 25 over 2 times pi. 12.5 times pi is give or take 36. So yeah, 39.6 looks good. One thing I will say is that when you start doing this stuff, it's a good idea to hold these as exact values as long as you can, and then find an approximation at the end. Right, so rectangle is then going to be... Hey, Zach! How's it going? Yeah, Meowweather, this is Zach, also known as e to the 2i pi. PhD recipient. Congratulations yet again, Doctor. Worked really hard for it. You deserve it. Who usually streams on Saturdays and I forget exactly when else, but that's just me. 156 sounds good. Yep. So base 1, again, showing work, right? Like, kind of important for me and for my students, what I tell them always. It's going to be 12 by 13. So yeah, 156 square meters. And then here we have a 1/2. Now what is the base and what is the height of the triangle? This is where showing your work is actually kind of important, to be like, oh wait, hang on, let me not like just give you the answer, because in this case this is a compound answer. There are actually two parts to this. And if you screw up one of them, I want to know which one. Now on a problem this easy, I could probably diagnose it pretty simply and just say, oh yes, I know exactly where you went wrong based on the answer you give me, if it's wrong. If it's right, cool. That's the other thing, is that teachers will want to see... Yeah, right. Teachers are going to want to see where it is that your understanding is. So, just to make sure that you actually get it, they'll want to be like, okay, let's see the intermediate step to say, clearly, this height of this triangle is going to be 4 meters. This base of the triangle is clearly going to be 12 meters because it's the same as the rectangle. Clearly. You and I can say that, right? So yeah. But then... You know, I had fairly comprehensively eliminated that from my vocabulary a year ago. Yeah. Well, Fizzbuzz, Meowweather's been in a professional career that does require units, so it's probably been ingrained. What did I drop? Gotta make sure both your clients and everybody else who's on the job understands what you're doing, because otherwise, oh man, I can imagine the yelling about wastage that the foreman would have. And always in millimeters, yep. So yeah, one more thing about triangles, right, is that since it's a triangle, we also have to have that half there. So, yeah, you're right, 100%, 12 by 4 is 48, but then just make sure you have the half of that, so. Always in electron volts. Right, so then area of the, nope, not a D, that is a semicircle. Plus area of the rectangle plus area of the triangle gets you your 25 halves pi plus 156 plus 24, that's going to be 180. Alright, 25 over 2 times pi plus 180, which is going to be approximated by, and now, yeah, everybody's favorite part. 25 over 2 times pi equals. Alright, 3927 plus 180 is going to be 219.27. Square meters. Right. So this is our area. And then when we go back and say, well, let's find the perimeter of this thing. Right? How are we going to work that out? Right, so how are we doing perimeter? That's interesting. Uh-oh. 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 Sorry, I thought I lost control of the window there for a sec. Boo. Nice. Yep. Find the hypotenuse of the triangle. So in order to get that 100%, this is going to be 12 squared plus 4 squared equals, we'll call this H. No, that's a terrible idea. We've used H all over the place. We'll just call that C. C squared. Alright, so 144.16. It's going to be 160 squared. Whoops, nope. 160 equals C squared. Okay, so then C is going to be equal to So what do we get?
No internet? No worries. With Spotify Premium, you can
1265 seems right. So here,
wherever.
right, we're taking the square root of 160. To get the exact value, we can take the square root of 16 times 10, which is the same as the square root of 16 times the square root of 10. Square root of 10 is not nice. The square root of 16 is 4. So 4 square roots of 10 is going to be the exact value, which again, you can then figure out approximately what that is, or just take the square root of 160 if you're just going to do the approximation. But nonetheless, yeah, 12.65. So the only reason that I am kind of picky about it is just that if you've got a lot of fractional pieces, they might end up adding up to skew your end result by just a little bit. So if you keep it as 4 root 10 or the square root of 160, and then we end up at the end adding up all of the little bits in the calculator, because the calculator can just figure all that out. We don't need to worry about like intermediate decimals. That's a terrible idea, right? If you don't know how to do it on the scientific calculator, you could do it on like Desmos or one of the graphing calculators or anything else. You plug in the whole thing and then it just spits out a value. So it deals with all of the rounding and everything like that. You don't have to worry about it. It'll get you something accurate to 10 decimal places. You might only need 2. So again, the problem here is that this is off by millimeters, right? 12.65 is off by maybe only like 1/10 of a millimeter, but nonetheless, it adds up. So every time we're off by a little bit, that error is going to keep compounding over and over again. All right, what else do we need?
You know what time it is. Marvin Devine, Huber, Axel, and you know how we do.
Oops. Yep. Perimeter of, in this case, well, it's not really a whole semicircle, right? It's just going to be the arc. Because we don't need the vertical part. So yeah. 1/2 pi times the diameter, which ends up being, again, 1/2 times 5 times pi, so 5/2. All right then.
You already know what happens when we link up. Let's go. Yeah, I got the juice. Yeah, I got the juice. With game cool, make them look like cool. Always play it cool, that's the biggest rule. Forget what they doing, keep on doing.
Oh, whoops. Pfft. Wow. Alright. I apparently left it as half 10 times pi. Thank you. It's gonna just be 5 pi. Okay. Right, so this is going to be important. Right, if you're approximating based on those rounded decimals, then adding these things together is going to cause potential. It's not like it's catastrophic, but you know, it's going to be off by a millimeter or two. So just be careful. So my recommendation, we got 5 pi, we got root 160, and then yeah. All right, then what? Yep. So just as a reminder, make sure you've got all of the straight bits in there. So we've got our 17 meters for the whole vertical side on the left. We've got 12 meters for the whole horizontal side on the bottom. And then we've got our 3 for the vertical side that's above the semicircle. We already counted the diagonal, and we've already counted the semicircle. So as long as you've got all these bits, right, that's 20, 32. Plus 4 root 10, again, root 160. Or use more decimals than you need for the other stuff, and then when you pile it all together, all right, what do you get? Oh, there you go. Yep. Okay, so here's where we differ. So by plugging in all of those values that I did here, this is 60.35707 meters. Right? So that 7, if we're looking to do it to 2 decimal places, would make it this a 36. So that's going to be 10 millimeters compared to what you gave me. Realistically, it's 7 millimeters off, or you're 7 millimeters off. I would be 3 millimeters off. It's probably within error of whatever the thing is that we're making here. But just as a decent reminder, make sure that when you do this, right, make sure you know how many decimal places you actually need. Yep, and try not to round before the end. So try to keep the exact values as you go through. If you need, right, you can just take the square root of 160 and like store that value somewhere. So actually, right, if I just hit 5 pi and then hit the M plus button, this takes that, 15 whatever, and puts it into the memory. So you can see like the MR button is lit up now. And then if we type 4 times square root 10, end parentheses, and then hit M plus. That should give us, adding those two numbers up, equals. Boo. Nope. Oh, there we go. Okay. It did it automatically. So when I just hit M+, it then added the number to the memory and then displayed what the individual number was rather than what the total was. Okay, fine. I can deal with that. And then I say take that number and add 32 to it, equals, and now we get this 6035, 6036. So using the M plus button, you could just immediately add up the next number every time you do this. So if I wanted to, right, clear all. Okay. So I hit, oh boy, 5 pi M plus 4 times square root 10. This is probably not showing up terribly well, but you know what? This will be fine. M plus. And 32. M plus. Memory recall. 60.357. So, perfect, right? If you just keep hitting M plus to all these things, I'm saying I want to take that number and I want to add it to the memory. And just keep adding it to the memory, add it to the memory, add it to the memory. If you come up with a negative number, you could say, I want to subtract that from the memory and hit M minus. Yeah, and I mean, depending on what it is, right? Because on this thing, do we really need to be accurate to the millimeter if the thing is 17 meters long in the first place? Or 3 meters long on that little bit, right? 3 meters is pretty big. So do we really need it to the millimeter? If it's something like an aircraft, you know, piece of a wing to an aircraft, then the answer is yes. Right? If it's just like I'm drawing out a line for a fun obstacle course on a sports field, like who cares? As long as it's close enough, we'll be happy with it. Yeah. Definitely worry about the use case. Okay, ads are about to start. We're going to go for 3 minutes, and then we will come back. Anybody has any questions, drop them in chat. We'll also poke on over to some of the Discord servers and see if anybody's got anything interesting. I might poach some of your stuff, Zach, sorry. At any rate. And you know what? It's even pretty decent to like get alternate viewpoints of stuff. So it doesn't necessarily mean that I'm poaching something. It just means that I might be giving a different take. Alright, see you in 3 minutes. Thanks everybody for coming by. See you in just a little bit.
Say I'm dangerous 'cause I to give me your loyalty, 'cause I'm taking the world, you'll see. They'll be calling me, they'll be calling me royalty. Best to give me your loyalty, 'cause I'm taking the world, you'll see. They'll be calling me, they'll be calling me royalty.
The year is 1991. Birds and people are living together in seemingly perfect harmony until one day a young man catches fire. This is Phoenix.
Hey everybody, welcome back. So, if anyone is interested in calculations, again, let me know. You can poke around our friends' Discord servers here and see if there's anything cool. Wahaha. Oh goodness. That's a lot of stuff. Alright, and if I don't know anybody, yeah, alright, there. Good luck out there. Have a good night. No problem. And like I said, oh, right, anybody else who's new also, we have our other friends who are here. Oh dear. We have our other friends who are here, affectionately known as the Math Chads. We also have multiple other people who are not on this list, and we've been trying to get like a third or fourth list going at some point, but a number of them are located at our central repository Discord server known as the Elements, run by Penn Center. So here, if you click on the Discord link, that is a permanent invitation to his Discord server, and at least I hope it is, and you should be able to get into it and see what's interesting. Okay. Interesting. Okay, so we've got a set of differential equations which are in Zach's server. Find the solution to the differential equation that satisfies the given initial condition here. So there are several different ways to do this. I was actually just looking at one of my N simplex pachinko differential equations class videos from this past summer, and or like summer fall, and we had done a, well, first of all, to classify this, right, this is a ordinary first order nonlinear differential equation. And so there isn't necessarily going to be like a single solution representation of this. I think this one is not too bad to figure out. However, because there is a y squared term, it kind of messes around with stuff. What I had actually been looking at was one of my videos, which was looking at linearization. Now, I grant you, this is not actually looking for a solution, but this is looking at what kinds of behaviors we see around each of the singular points. So what this is doing is it's going to say, what is y prime going to be equal to? So dy dx. So if we move our plus y to the other side, we get y squared minus y, all divided by x, which is also known as y times y minus 1, all over x. So the important question then that we start with is, where are the singular points of this particular setup? So like we get y prime is equal to 0 at all of these things, or is non-existent where? Well, that one's easy. This is going to be undefined at x equals 0. So this is going to have a vertical slope. And actually, I might not be entirely right about the linearization. That's fine, because that was looking at first order systems rather than yeah, that was looking at first order systems rather than a first order differential equation. So it's alright, but we'll figure it out. So y prime is equal to 0 when, or that's going to imply that y is equal to either 0 or 1. Right, that is the only location. Our numerator has to be equal to 0 in order to make the fraction 0. And that only occurs where y is either 0 or 1. So that is a horizontal slope. Those are the only places where this sort of behavior happens. So we can then draw a graph for this. 0 and 1 and x equals 0. Okay. slightly off center. Yeah, that's fine. Alright, we have an undefined slope where x is equal to 0, so we have vertical slope. And then we have a horizontal slope at x equals 0. And also at y equals 0, and also at y equals 1. Okay, now this creates a problem, or rather a conflict, at 0, 0 and at 0, 1. Because at both of these locations, we have an undefined slope value. And I don't just mean like it's a vertical slope value, like no. We get both an undefined vertical slope and also a horizontal slope. So that's conflict. It tells us that those particular points are completely meaningless. If we found ourselves at either of those points, they are going to be equilibrium points. So nothing's happening. We would stay exactly there, completely in balance with the whole system. There is the possibility that those would be unstable points, and so they would fall away about as, they would just fall away from those points. That would be very much the same as where JWST is located, the James Webb Space Telescope. It is currently located at Lagrange point 2, I want to say. Nope, not that. Yep, Lagrange point 2, which is located on the opposite side of the Earth as the Sun. And it balances all of the gravitational forces. However, if something were to just be slightly off of the L2 point, then it's going to feel a pull away from that particular point. JWST is in an orbit around that particular point, which ends up making it slightly more stable overall. Rather than trying to just sit at L2, it's going to then orbit that point, and it's going to be able to stay more or less in orbit for a longer period of time before it starts drifting away. Okay. So we don't know whether this is going to be at least not at this exact moment in time. We don't know whether this is going to have positive or negative slopes or anything like that. So what we should do then is look at what the values are going to be for each x's and y's in each of the regions that are here. We have 6 different regions. So something that is back here is going to have a negative x value and a large y value. Right? Or at least bigger than 1, but we'll just call it large. In that region, our x value is negative, so our denominator is going to be negative. Right? Our numerator is going to be a positive times a positive. So this is overall going to be a negative value, which means that as we get really close to this 0 value for our slope at y equals 1, y equals 1, y equals 0, x equals 0, right, as we get really close to y equals 1, all of our slope values should be negative and should be fairly flat. as we get closer and closer to x equals 0, our x values in the denominator get really small, which cause the overall fraction to get really large. So this is going to become a larger and larger value, steeper and steeper. And then as we increase our y values going up, those are in the numerator. So they're also getting steeper because of the y's. Okay. Now, realistically, if we're doing this particular problem, we only have to worry about the values that are close to here. So y equals 1. Oh no, sorry. Y of 1 is equal to -1. So where's that? That's at location 1 comma -1. Right, xy. But I do find that coming up with the rest of the behaviors of the rest of the slope field is helpful in order to understand everything a little bit better. So realistically, right, 1 comma -1 is down here. Dot. That's our initial value. We only have to do stuff that's within that region. Right, y prime is equal to, this is a y value that is negative times a y value, a y minus 1 value that is negative, divided by an x value that is positive. And so overall, this is going to get us a positive slope value. Again, as our y's are negative and are moving upward, they're getting smaller and smaller and smaller. And our x values, as they decrease, getting closer to 0, they get larger and larger. Alright, so these are practically vertical, and then they flatten out pretty quickly. So what do we see here? This solution that starts at 1, -1 is most likely going to have a curve that looks something like this. This is the solution curve. To that differential equation that's up here. Now, how particularly helpful is that? Not super, but it at least gets us a sense of what the behaviors are, where we're starting, where we're going, where we came from, that sort of stuff. And also not that one. If we look in this region here, y prime is going to be equal to, our y values are positive, our y minus 1 values are negative, and our x values are positive, which overall gets us a negative. Again, as we go further to the right, our x values are going to increase, which causes the denominator to increase, which causes the overall fraction to decrease. So we get something that's almost flat. And then as we move closer and closer to our y-axis, x equals 0, this is where we get larger and larger slope values. But then, again, we get a balancing effect as we get closer to y equals 0, which is going to get us a 0 slope again. Up top we get y prime is equal to, this is where our y values are all positive, y and y plus 1 values are positive, and our x values are positive, so we get an overall positive value. So again, starts out really close to 0, but positive, and starts increasing faster and faster as we get close to 0, 1. As we get close to x equals 0, that gets steep, and then as we get further away, we're going to start decreasing. That y prime is equal to. Down here we have y values that are positive, y minus 1 values that are negative, and x values that are negative. So here we get an overall positive value. Again, shallow until we start getting close to x equals 0, at which point it gets much steeper. As we move up, these values start becoming steeper faster, and then it's going to start becoming close to 0 again down here. And y prime is equal to, at the bottom left corner, we get negative times a negative over a negative. This is where we get the overall negative value. Again, as we're close to y equals 0, we get negative values. As we move down, our y values will decrease, but the size of them increases significantly. And then as we get close to x equals 0, it starts increasing a lot. So this is what we have. So this is our differential equation. So 0, 1. Right. It's hard to classify these because, like, time is kind of our independent variable. And then 0, 0. So around around 0, 0 we have what's called the saddle point. So stuff that's around it here is going to essentially avoid 0, 0. So it never will end up hitting 0, 0 itself unless you start it at 0, 0, at which point you just don't move. Most likely. Our dx, or delta x, we don't really have any like information on it. So we just kind of like assume that that's what's going to happen. Whereas 0, 1, it's kind of a source or a sink. Like the stuff that's coming, right? There's going to be stuff that's coming off of it or going into it, question mark. Right? The real question is what's happening with dy versus dx. And so it's kind of hard to like balance what we're talking about. It'd be a lot easier if we were talking about a first order system, which includes time as its independent variable. So then we'd be able to say, okay, as time increases, then we would be coming into or away from each of these values. So 0, 1 could either be a source or a sink. Either stuff is going into it or stuff is coming out from it. 0, 0, we have these saddle points. So everything is kind of avoiding this particular point. It's probably not even appropriate to call it saddle point and all that. Right, stuff is trying to avoid 0, 0. So this is really an unstable equilibrium. Right, so like as if you just move slightly off from 0, 0, then you're going to go away from where we are. You're going to follow a different path, which is not going to bring you back to 0, 0. Right? And we can even look at this in terms of no, I guess we can't. What would happen if you went slightly off in the either directly horizontal or directly vertical positions? Like, where do we go if you're just perturbed slightly away from this particular point? And, well, the answer is I don't really know, because at x equals 0, we have a 0 in the denominator. So that's not really helping us tell which direction it's going. In theory, right, in here we get in here we get 1 positive and 1 negative. So like that's a negative overall value. So I want to say that this is undefined, but it's moving downward. And then up at the top, we have a positive times a positive. So overall, this is going to be an undefined value, but positive. And then at the bottom, again, in theory, this should be a negative times a negative. Oh, yeah, no, that's okay. Negative times a negative, which is a positive value, which is saying that, like, sure, it's undefined, but things are going to get moving upward. Well, that makes it a stable equilibrium from those directions. That's awkward. So overall, that would make it semi-stable, but that's a pain. Right, this would also make it a 0 in the y's, the negative versus a positive in the x's. Nah, I don't think we can do this, actually. I'm not sure we can even call it an unstable equilibrium. I think we just call them equilibrium points and move on. Just because, again, we see that we've got two different behaviors that are going on at the same time. So, slightly annoying. Anyway, if anybody has any questions, we can look at stuff. I actually do have a nonlinear differential equations textbook. I don't remember. It's been such a long time. I don't remember how we're, supposed to solve nonlinear if the rest of it looks like pretty decently easy. Oh, come on. Oh, I just pushed it in further. Differential Equations, Dynamical Systems, and an Introduction to Chaos by Hirsch, Smale, and Devaney. Alright, first order equations. Nonlinear systems, there we go. Ooh, bifurcation diagrams, that might help. Oh no, that's nonlinear systems. We're not doing nonlinear systems. So we're just doing chapter 1 stuff. Constant harvesting, bifurcation. Okay. Poincaré map. No. See, this all looks the same in terms of trying to find stuff with like parameters that are thrown out there. Okay, this is all single variable stuff. No, now we get systems again. This is really not helpful. Okay, so first order equations. Nope. Not it. Yep, we don't want systems again. So many systems. Man. y prime was a function of y divided by x times 1 over x. Alright, let's look real quickly at what Wolfram would do with this. So, y prime, xy prime, x and, no, x times y prime plus y equals y squared. Yeah, that would be separable, wouldn't it? Oh, man. That's not that difficult. Man. Okay. So this was y prime divided by y1, or y minus 1 is equal to dx over x. This could be shifted not to y prime, but dy. And then literally just take the integral of both sides. Ugh, God. Right hand side becomes natural log absolute value x. Left side, we have to separate this by, who's it? Decomposition. Fraction decomposition. Partial fraction decomposition. There we go. This is going to be a over y plus b over y minus 1 is equal to 1 over the product. Okay, which means that this is going to be 1 is equal to y times a divided by y goes away, and we just get a times y minus 1. Plus b times y minus 1 divides out from both, and we're just left with by. Okay, at y equals 0, we get negative a equals 1, so therefore a equals negative 1. Cool. At y equals 1, we get by equals 1. No, b times 1. So b equals 1. Therefore, this is going to be the integral of negative 1 over y plus 1 over y minus 1 dy is equal to the natural log of the absolute value of x plus c. This is going to be a negative natural log absolute value of y plus natural log absolute value of y minus 1 is equal to the natural log absolute value of x plus c star, which technically is the same. It's just a constant. We don't really care. Just don't mix it up with that one. Those are not equal to each other, but it doesn't matter. This is y minus 1 over y is equal to cx. And again, this is a new double asterisk constant. It's just a constant. It doesn't really matter. That's easy. Correct. 1 minus 1 over y is equal to, I'm just going to realign, call it cx. Swap locations. So this is 1 over y is equal to 1 minus cx, which again now can just become 1 plus cx because that's a constant. Now y is equal to 1 over 1 plus cx. Okay, where y of positive 1 was equal to negative 1. So negative 1 is equal to 1 over 1 plus c times 1. Guess I could have just done that back up there somewhere. It's fine. Let's get rid of that one. Just make it easier on ourselves. Do this one. 1 plus c times 1 is equal to 1 over negative 1, which is negative 1. Subtract c is equal to negative 2. Therefore, y is equal to 1 over 1 minus 2x. Bit of legwork, but worked out alright. This is separable. So because you take this differential equation, you can separate it by trying to get all of the y's on one side, all the x's on the other. The way to do that here, mean as it is, gather all the loose y terms together and then divide them off of your y prime, which you can change to dy, and then the x's all become their own thing on the other side. Split y prime into dy dx, and then split where your dy and your dx are going. Alright. I think that'll do us for tonight. So. Gonna find somebody to write out to. Hopefully math. Oh dear. Somebody's playing Yes Your Grace. Excuse me? Oh, okay, good. I was looking at a piece of news, which I was worried. I'm not seeing anybody who's doing math directly. Oh no, wait. Dr. Gold. But he's been on for 2 hours, so there's a good chance he's leaving. Let's go look at paleontologizing. This is Dr. Danny Anduza, who is a paleontologist, who has just been talking about the Troodon. Those of you who were friends of Dino Dana back in the day, or Dino Dan before that. This is a science stream. He has been on for 4 hours currently, but looks like he's still going. So we'll head on over, and I hope to see you all on Wednesday for some more math stream. This is going to be more calculation oriented, so more of what you've been seeing tonight, really. Maybe we'll talk a little bit about curriculum, but mostly it'll be calculation. And if anybody has any questions, feel free to drop in, send some questions over, and I'll be happy to answer. We will be back on Friday with gamey type stuff. I suspect we're going to be playing... Oblivion. Yeah, I think we're going to do Oblivion on Friday. So, hope to see you all later. My name's Obi-Wan Pez. This is N-Simplex Pachinko. See ya.
Love You is out now. Listen and follow on Spotify.